Okay, so it's a great pleasure to welcome Niklas Beisert from the Max Planck Institute, who will continue the story of integrability in AdS CFT with focus on the S matrix and algebraic aspects.
Okay, thank you very much, and it's also a pleasure to be here and enjoy some of England's weather this morning. Though I mean, it was never as bad when I studied here for almost a year. I was perhaps lucky. So I'm going to continue the lectures on AdS CFT integrability, ones that Konstantin Zarembo started. So so integrability is not only a terribly useful thing when you want to compute things like the spectrum, as hopefully Zarembo has told you or showed you, but besides it's also a very interesting symmetry, and I'm going to talk about the symmetry. Symmetry is actually a very large symmetry which almost constrains most of the dynamics of the system so that you can actually solve things efficiently and, well, almost completely. So my talk will be about mostly about symmetries in this business. So symmetries are perhaps a bit of a math subject. This is a bit of a math institute, and me being a physicist and well, talking about math will probably make the physicists as well as the mathematicians among you well, not very happy with this lecture because, well, it's probably not very rigorous and it's probably a bit technical. So, but anyway, you're stuck with me, as Minola said this morning, for the next 3 lectures. But anyway, please interrupt me as you interrupted all the other speakers all the time if something is not clear. Okay, so the outline of my lectures will be 1, the S or the R matrix and how to construct them from scratch, and what this has to do with Yangian symmetry. It's a very, very beautiful symmetry. I hope I can spread some enthusiasm among you on this. And the second lecture should be about the S matrix of AdS CFT. Should be some overlap between the lectures. Well, here I want to start with something well, really sort of from scratch. The Zarembo's lectures should be very useful to understand many of the things, but I try to make it as simple and pedestrian as possible. And, well, the third lecture will be a surprise. There are many reasons for that, one being that I didn't quite know what Zarembo talked about. The other one is, well, I haven't actually prepared it. And the third one, and probably the most realistic one, is that I'll never get there anyway. So, okay, let's see. But anyway, I think if you have some questions concerning Zarembo's lectures, I'm happy to explain them in perhaps different words. So if anything comes to your mind, then perhaps at the end of the lecture or even now, you can just tell me. Zarembo's not here. He's not watching. It's not only Big Brother. So, he might. Yeah, no, he's not watching. So you can complain. Probably has nothing to complain about. Okay, so I wanted to end at well, about 1 hour and then maybe leave some time for questions. But it's much better if you interrupt me and don't leave the time for the end. So, okay, let's start. So the first lecture will be about the S matrix and the Yangian. And so let me just tell you the setup of the physical model that I will be talking about. So that's the particle model setup. So consider, well, we have some particles which live on a line. These particles have a certain momentum. Each particle has a certain momentum. Let's call it P and Q. Often I'll have only two particles, so I'll denote the momentum by P and Q. And then we have flavors. I might denote them by A and B. Okay, so that's the setup. The flavor should run from 1 to n, with n types of flavors. And I want to look at a model which has SUN symmetry. So it's not too hard to figure out how the symmetry is realized on these particle flavors. Okay, so what does this have to do with gauge theory and string theory? Hopefully Zarembo has explained this in the coordinate beta. So for spin chains or gauge theory, you use the coordinate beta ansatz. Where essentially, well, you start with a ferromagnetic vacuum where basically you have all the spins aligned, only a few spins are flipped, and then you would somehow identify sort of a particle with a spin flip. Draw them. So a spin flip would be a particle, and you look at a linear superposition of these states where this particle has a certain momentum p, or this would have a momentum q. Well, in this context, these guys would be called magnons. Magnons, particles, excitations. I should use these words interchangeably. And then for string theory, well, you might think about string theory in 26 dimension, but essentially you could just consider a piece of string and say you take this piece of string and wiggle it a bit, and then some excitation rolls down the string, and this you could, roughly speaking, identify with the particle excitation. So also has, say, momentum p, and you could have many of them traveling with different momenta. Well, in this setup, you would have, well, in gauge theory, if you use, well, you have all the different scalars, and putting different scalars here corresponds to the different flavors. And in string theory, you have all the 10 directions in your space. So some of the transverse directions will correspond to the flavors. Okay, so this is, roughly speaking, the setup, but essentially you can think of a one-dimensional particle model with particles which have n flavors. Okay, so that's that. A single particle shall be denoted by PA. So this is the momentum, and this is the flavor. And multiparticle state would be denoted by PA QB, where this is supposed to mean that this particle with momentum P is to the left of Q. So P is left of Q. Well, that really doesn't make total sense because, well, I mean, you can't have both a momentum eigenstate and say which particle is to which side of it. But what I mean here is the projection of a state with these momentum to those where the particle P is left of the particle Q. So you could also think it's is actually very much left of Q. So so you'd think of a wave function e to the I p x e to the I q y x y integrated over x dx dy, x much less than y. Yeah, right. It's I'm talking about infinite linear chain or infinite piece of string, and these states are sort of asymptotic states where the particles are well separated. So, right. So why does it make sense to talk about asymptotic states? Well, I will consider this the interactions in the model to be local. So whenever the particles are not very close, then they will not interact. So it makes sense to talk about asymptotic states. And in fact, so when you have a state with two particles of momentum p and q, so this is say this setup, and this will typically not be an eigenstate of the system, but you should supplement it with a state where the particles are interchanged, q and p, like this. And, well, I mean, in a free model, this together would form an eigenstate, but because you have interactions, you should insert a certain phase here, e to the I phi, say, which tells you sort of the phase shift you get from making one particle pass the other particle. And this phase is, you could also write it as S, and because these particles have flavors, this will be the S matrix. S matrix or scattering factor. So in such a particle model, you would, generic eigenstates you would compose from these asymptotic states, and the phase, well, tells you everything you need to know about the asymptotic behavior of, or the infrared behavior of the model. Okay, so are there any questions at this point? Good. So I want to talk a bit about the symmetry. You have SU n symmetry. That means you have the generators, let's call them JA, where A runs from 1 to n squared minus 1, which is the dimension of this group or algebra. And you would have certain Lie brackets, JA with JB as IF, AB, C, JC, the standard thing. Well, for SUN, you can use a different basis. If you want a bifundamental basis where you write the generators as JAB, AB run from 1 to n. Now you see in total this would give you n times n different generators, so n squared, so there's one too many, and you make the constraint that the trace of these generators is 0. Okay, so this is a different basis which I will mostly use. The action on the on these particle states is defined as follows. So that would be a representation. On a single particle, you have that JAB particle with P, momentum P and flavor C. Well, it's given by this CB. Phi A minus 1 over n delta AB state C. Actually, I forgot to write down the commutation relation in this basis. So so the Lie brackets here are JAB with JCD equals delta CBJ AD minus delta ADJ CB. And you can easily verify that these generators obey this Lie, or this representation obeys that Lie bracket. Okay. So that would be the action on a single particle state on. Oh, this is. I was too used to that. This is P. So so that means the SUN symmetry is an internal symmetry. It doesn't touch the momentum of the particle. It just transforms the various flavors among each other. For multi-particle states, you would get that JAB, say PC, QD, dot, dot, equals, well, it's essentially just a tensor product. So you act with, so you transform this particle, PA, QD, plus delta dB. Then you transform the next particle, PC, QA, dot, dot, and then finally you have to subtract this trace again. I mean, this term is just there to make these generators obey this rule. So when you take the trace here, this will become itself, and this will give a factor of n, so this thing cancels. So here you would have to subtract the total number of particles, delta AB, times the state. So this is just how the symmetry would act on multi-particle states, and it doesn't really distinguish between the particles. It just transforms each particle individually from all the others. Okay. So now let me talk about scattering. So when you want to form this this state here, so you would write, or this eigenstate. So if you have PQ plus this e to the I phi QP, you can write this in an operatorial way by replacing this by the S matrix. So this is scattering. So you would write this as PA QB plus the S matrix acting on the same state. Right. So this would be a proper eigenstate of your system. And so the problem is to, well, obtain this S matrix somehow in order to understand. Pardon? I don't want this. I mean, here you do this. This S matrix is supposed to interchange the particles. Maybe just a notation. So I will define this S matrix to act on a state PA QB just as some matrix. Let's call it R A B C D, depending on the particle momenta P and Q. And then this is Q D P C. And so this would be, in some sense, a flavor-dependent phase factor. So sometimes it's convenient to introduce the R matrix. So the R matrix will be just defined as a permutation operator times the S matrix. So, well, this R12 on PA QB would just act as RAB CD PC QD. So the S matrix here interchanges the two. The R matrix wouldn't do that. That's really the only difference between the two objects. But often it's useful to consider the R matrix. So our aim will be to construct the R or the S matrix, well, from scratch or from symmetry. I guess Zarembo also derived an R or an S matrix maybe for the Heisenberg chain. I'm not quite sure what he did, but he derived it sort of from the physics, from the spin chain Hamiltonian, or yeah. Whereas I want to construct it from the symmetries of the system, or basically from the integrability of the system. Okay, so what does the symmetry mean? The symmetry of the S or the R matrix means that these generators J, A, B should commute with the S matrix. Or if you want, with the R matrix. Okay, fine. So let's see what this gives us. What sort of constraints this gives us. So let's act on a two-particle state. So let's take one part of this commutator, JAB S12, acting on PA, PC, QD. Well, what does this give us? Okay, first you act with the S matrix. You evaluate it like up there. This gives you A, C, D, E, F, P, Q. Acting on Q, D, P, C. And then you act with this on this two-particle state. that would give you delta A. Let's see. Delta D. Okay. So this gives you FB RCD that plus delta EB right, and then there's also this 2 over n term, which is not really important. Now, if you act in the opposite order, on this state, you would get S12 delta CB PA UD plus delta DB PA C Q A. Okay. And then you have to act with the S matrix on this state and on this state. So that gives you 2 contributions, CB, R, P, Q. What are the indices? You take AD, just what you find here, EF. Q, F, P, E, plus delta D, B, R, C, A, E, F, P, Q, Q, F, P, E. Okay, so it was a bit of work, but, and then there's, shouldn't forget this term. But in any case, this term equals that term, and now you have to make all these 2 terms equal those 2 terms. And well, when you collect the terms, you'll find a constraint delta AF R CD EB plus delta AER CD BF equals delta CBR AD EF plus delta DB RCA EF. So in fact, lots of different indices, which is not too transparent. But there's a simple solution to that. Yeah.
Sorry, just ask. Didn't you have to assume along the way something about the dependence of R on P and Q? I mean, is there like
the dependence on P and Q is always the same.
So you can just exchange them.
Well, I'm the only thing that exchanges things is the S matrix, and the S matrix produces the factor with R, P, and Q. If you had 2 S matrices, it would matter, but here you have just one, so the order will always be P and Q. These things, actually, these generators don't care about the order, so that's why you don't quite see it. Okay. So the solution is actually not that terrible. R, A, B, C, D, P and Q equals, well, some function R1 depending on P and Q. You don't quite know that. I mean, the only thing that matters here is how the indices are connected. And, well, the momenta don't really go into this. So either you connect these two indices or you connect the other two indices. A, B, D, and therefore you get two functions that you don't quite know at this stage. In Q, A, D. So now you cross these two indices. Actually, well, you might also pull out a common function. You could write some function g of P and Q as a global factor, and then write f P and Q times delta A B, delta B D plus delta AD delta BC. So actually this function equals that function. Or you could write it in an operatorial way. You could write R12 equals G P and Q. Now this here just essentially exchanges the indices between the two sides. So A connects to C, A connects to D, and C to B. So you could write this term as a permutation operator, and this term PQ as an identity operator. So that form you get from the group, from the SUN symmetry. So it solves most of the matrix structure, but you are still left with two functions that you don't know. Actually, why do you get two functions? Well, you deal with two fundamental representations, which in Young tableau language you could write as this, and as you might know, this tensor product gives you two components. One is the symmetric combination, and one is the antisymmetric combination. And for each of these two components, you get one function that you don't know in this R matrix. Okay. So I hope you've seen an R matrix of this form already. Now, of course, we need to fix these factors, and for that we need further properties of the R matrix or of the S matrix. And well, the most prominent one is the Young-Baxter equation. So the Young-Baxter equation is given by that is R12, R13, R23 equals the same thing in the opposite order. And what does it mean? Well, you essentially, when you talk about factorized scattering, that means in terms of two-particle S matrix. So when you have a scattering process which you can factorize like this, right? Where, well, let's see. So you first act with 2, 3. So this might be line 3, this might be line 2, or particle 3, 2, 1. Then, well, this particular scattering process where you take 3 all the way here, 1 all the way here, and 2 all the way here, you can factorize in terms of these 3 two-particle S matrices. But you could also factorize it in a different way, namely by, let's see where I put it. Like this. So this is still line 3, 2, 1, 1, 2, 3. But you see the order of the scatterings is different. Here you first scatter 2 with 1, and then 3 with 1, and then 3 with 2, like this. So for consistent factorized scattering, you need this condition. And now you can plug in this above expression for the R matrix to see if it gives you any constraints. So let's do that. R23 minus R, well, let's see. So let me take the difference and demand that the difference is 0, and then, well, the R matrices are all proportional to G of, well, different particles. So let me just divide by this. This makes it much simpler to evaluate. Okay, and then each R matrix in this case consists of 2 summands. So you have 8 terms from here, 8 terms from there. And so let me just write down those terms that don't immediately cancel. Otherwise, I spend even much more time on writing down these things. So one thing that doesn't immediately cancel is if you take this term for all 3 factors, the P12. So you would have that P12, P13, P23 minus P23, P13, P12. And then there are some more terms. When you have 2 P's, 2 permutations, and one function, this gives you, well, let me write it down. P12, P13, F23 minus P23, P13, F12. So these are the 8 terms that that survive. All the other terms have only 1 permutation, and well, you can immediately. Well, it's not too difficult to see that you always get two matching terms. In these diagrams, well, you look at a scattering matrix. Well, let's call it S. Which scatters 3 particles from this particular order to that order. Now you look at factorized scattering. I mean, in integrable systems you have factorized scattering. So you want to express this 3-particle S matrix in terms of a product of two particle S matrices. That means the three particles don't just scatter all at the same time, but they scatter pairwise. And so first you could scatter these two, 3 and 2. Then you have then you scatter, say, 3 and 1, and afterwards you scatter 1 and 2, which is just this the sequence of R matrices. So R23 is this, then R13 is that, and then R12 is that. But you could also start not scattering these two, but scattering these two first. And when you do that, you get this expression. And if you agree that these are matrices, then they will not just commute.
Okay,
So
the direction of time kind of flowing systematically.
it's not really, I mean, you might think of it, I think many people think of it that way, but essentially it's just you have this asymptotic state where the particles are ordered 3, 2, 1, and you have this asymptotic state where they're ordered 1, 2, 3, and you want to know the relative phase factor between the two. And this is what, I mean, this gives you the relative phase factor, this gives you also the relative phase factor, and for consistency they better be the same. Good. So so we're left with this, all these factors. Well, you might hope that perhaps this F12 cancels with this, but you see these two, these permutation operators don't just commute, so they don't cancel. So let's see how you can cancel these. So for this term, you would use the rule, say P12, P13. You can sort of take this permutation to this side and write it as P13, and then in this expression you have to exchange 1 with 3, and well, 2 doesn't appear. So when you take this over here, this thing will become P1 goes to 3, so P32, which is essentially the same as P23. So let's use these rules to relate these two terms. So when I take this 2, 3 to the front, then this term will be, well, 1, 3, and this will be 1, 2. And it's exactly the same as this. Everyone agree? So so this cancels with this term. Now, here, what do you do here? Let's try to bring it all in a form where you never have the P1. Oh, let's see. So let's say I don't like P13. Let's get rid of the P13s. So if I move this over here, this will become so this would be 2, 3. So here I have 2, 3, and 1, 2. Here, let's move this over here. So then 2 with 3. So this is 1, 2, 2, 3, and so on. I mean, you can always take this form into either P23 or P23, P12, or P12, P23. So what this boils down to is, well, I hope I get the signs right, but it should be F13 minus F23 minus F12, which multiplies P12 commuted with P13. So this Young-Baxter equation holds if this combination is 0. So how do you solve this equation? Well, let's just take this to the other side. So we have the equation F12 equals F13 minus F23. So that means this is actually a function P1 with P2, It's in a short notation. So we know that the function at points P1 and P2 equals this. So let's just fix P3 to anything we like. So this would be f P1 P3 minus f P2 P3, and so if we then define this as f of P1 minus f of P2, then this is sort of the solution. So we could say P3 is actually 0 or something else. I mean, this equation must hold for all values of P3, so we can also set it to 0, say. So the solution will be that that the function f of P1 and P2 is actually just the difference of two functions of the momenta. And that's what the Yang-Baxter equation tells you. So this function must equal f of p minus f of q, otherwise you don't get factorized scattering.
Why do you want factorized scattering?
Okay, I'm probably turning the logic of Zarambo's lectures around. So hopefully he has convinced you that the AdS CFT, planar AdS CFT system is integrable. Well, I want to say I start with an integrable model and then sort of reconstruct.
Factorized scattering is part of an integral model?
Yes.
By definition?
Yes.
Foster did explain in his lectures how it was related to the conservation of the individual momenta of the particles and
Yeah.
how that corresponds to higher conserved charges.
Okay.
Go with that.
True. Yeah. If you have if you have many conserved charges, then sort of for each conserved charge, well, essentially it translates to all the particle momenta being preserved. And if you have that, then the only thing you can change is actually the order of the particles. You can't move momentum from one particle to the other continuously, but you can only exchange particle momenta. And that leads to, that means that scattering is essentially just permutations, and permutations must obey this factorized scattering. So what do I want to say? Right. So we have R12 being G of P, G of Q times F of P, permutation plus F of P minus F of Q times the identity. How do we get this here, this prefactor? Or what can we say about it? Well, there's another process for factorized scattering, and that's the following. When you have two particles which scatter this way, like this, then what have you done? You take this particle from here and move it back, and take this particle from here and move it back. So actually you haven't done anything. So for consistent factorized scattering, this better be proportional to the identity. Which is also known as some sort of unitarity. Right, so the condition is R12 times R21 equals the identity. Okay, you plug in this, you'll find in the end that G12 times G21 equals 1 over 1 plus F12 F21. Okay, but you know that F12 equals F1 minus F2. So this equals 1 over 1 minus F12 squared. Changing the order just introduces a minus sign. So you write this as 1 over 1 minus F12 times 1 plus F12. And you could write it as, well, now you can change the sign again. Now you could write it as 1 plus F21 times 1 plus F12. Okay. Now the solution becomes obvious at this point. Namely, you'll find that G12 equals 1 over 1 plus F12. Actually, you don't quite know this because in this combination you project out something. So you can write something here that's projected out in this. So that means R012 times this must equal 1. So this is some homogeneous solution. But in total you get that R12 equals, now you have a permutation, this together, plus F1 minus F2 identity, and then you divide by 1 plus F1 minus F2. And you multiply by this, well, overall phase factor. And just by unitarity in the Young-Baxter equation, you can never fix this factor better than this. There are some other constraints that you can use, but you can't use it. So, yeah.
Could you motivate why do we have to impose unitarity? Because, well.
Okay, I mean, it's just this.
I mean, if you just scatter twice the particles, you just get twice the phase.
No, the point is you want to relate an asymptotic state where the particles are ordered in this fashion. So particle 1, particle 2, with an asymptotic state where they are ordered 1 and 2. So you want to relate one state to itself. So what's the difference of phase factor? What's the quotient of phase factors of these two states? It's 1. I mean, you just you relate one state to the same state, so it must be 1.
But here the change is not periodic.
It doesn't have to do anything. I mean, I'm just not talking about periodic chains. I'm just talking about infinite system. That's why I'm saying it's not particularly useful to think of this as time. Because I mean, in a classical world, if you have two particles scattering, then they are past each other. They will never scatter again. But in a quantum mechanical world, you could think these particles scatter back. But for consistency, you have to demand that nothing has happened along the way.
It's usually automatic if the underlying Hamiltonian is Hermitian. Respect.
It doesn't have anything to do with hermiticity.
Sorry?
This is not really unitarity. There are two notions of unitarity, unfortunately. One tells you that the S matrix is really unitary in in the usual sense, and this is ensured by a Hermitian Hamiltonian, whereas this guy here is
It's not
something.
the same?
It's not the same. I'm just saying. I mean, there's no complex conjugation involved, so it can't be. You might interpret it as, well, perhaps conservation of probability, because sort of I haven't really done anything here.
That's the usual interpretation of ordinary unitarity.
Yeah, you're right.
So this second condition, it has nothing to do with integrability. Is it only a consequence of two-dimensional system?
Well, it's actually, I mean, okay, let me put it straight then. Assume you have conserved, all the particle momenta are conserved, but not the order. So the only thing you can change is the order. And that means you have a permutation group. A permutation group is generated by nearest neighbor permutations, if you like. So the R matrix is a nearest neighbor permutation. And a nearest neighbor permutation must obey the following rule, that if you apply it twice, it's the identity. So I apply a nearest neighbor permutation twice, I must get the identity. It's also here for the Yang-Baxter equation. If you have three nearest neighbor permutations acting in this way, it must be the same as this. It's just a consequence of SK symmetry.
So tell me if I'm wrong. I thought that this first condition
Yeah.
is really a consequence of integrability. That it doesn't matter how you open up this multiple interaction. While the second condition is really a consequence of two-dimensionality, that you can't have an inelastic scattering. That, you have, well, actually a
I think this one is also it's quite essential that you have two-dimensionality for this. Because, I mean, if you don't have two-dimensionality, then there's no real notion of order.
So we are in two dimensions. Do you need integrability for the first, or for the first and for the second, or for neither of them?
Well,
Or is it just a consequence of being in a 1 + 1 dimensional field theory, full stop?
I would say this is a consequence of two-dimensionality by itself. Yeah. Well, I mean, if at least you have two conserved charges, which is the momentum and the energy, then you have this, definitely. This one leads to integrability. But this one you should also do. Often, you don't really need to do it in all cases, but a proper definition of R matrices has this. And also, if you look at the pole structure of the R matrix, it's actually important for the understanding. So as we are asking questions anyway, is there anything I should, if I ever get to a third lecture, should comment upon or clarify from previous lectures? Okay, then I can continue a bit on this subject. This what depends?
Zero. The overall phase depends only on P and Q.
The overall phase depends on P and Q, right? It's a scalar factor, it's not a matrix. Quite right. So, by doing these computations, well, what have we gained? We have gained this S or R matrix in a quite explicit form. We don't really know. We don't know what this function f of p is, but this is sort of in the physics of the model. The physics will tell you how this function depends on P, but otherwise, and also this overall phase factor will somehow depend on the physics, but that's the only thing allowed from physics in this integrable system. But in doing that, well, we had this nonlinear Yang-Baxter equation, also the unitarity. Is not linear. So, I mean, here it was simple because the R matrix was not so complicated, but imagine you have more complicated groups and more complicated representations, then you're virtually unable to solve the Yang-Baxter equation from just looking at it, because it's a cubic equation, and well, it was more or less luck that we could solve it easily. Okay, so we get all these constraints. There's some permutation group symmetry which leads to Yang-Baxter equation and this unitarity. But it's not very much of a symmetry. I mean, it's just some discrete symmetry, which perhaps you think there should be more. And in the end, we find that this R matrix is a function of P and Q, and we don't know why. I mean, the symmetry didn't have anything to do with P and Q so far. I mean, maybe this SK, this permutation group, acted on P and Q, but otherwise, these things don't have anything to do with the symmetry. So why does it depend? And is there an algebraic notion for P and Q? So is there an algebra that also gives us the origin of P and Q? And for that, we can look at the loop algebra. So in fact, well, the answer to these questions would be the Yangian. The Yangian explains all of these features and gives us a better way of solving the Yang-Baxter equation. Hopefully I get there. But let's start first with the loop algebra on which the Yangian is based. So the loop algebra, in this case for SUN, is the following thing. Perhaps I can go through that and then stop. So you have generators J, A as before, but you now supplement them with an index n, where n is just an integer. And you would identify, well, this is called the level, I guess. The level 0 you would identify with the SUN Lie algebra. So you have, in some sense, you have infinitely many copies of this Lie algebra. And the commutation relations, or Lie brackets, are as easy as it can get. JAM with JBN gives you IFABC, JC as before, and you just add these guys. Well, I guess it's quite similar to string oscillators and also has some resemblance to the Thora algebras. Not quite, but so assume you have such an algebra. Then you can construct evaluation evaluation representations. So let's act with J JAM on this one particle state with momentum P and flavor A. So this evaluation representation would be given by some function of this particle momentum P to the mth power times the action of the Lie generator on this state. Now, not a big problem to convince oneself that this commutation relation is okay with that, because, well, I mean, you just let two things commute, you get the commutation relations of the Lie algebra, and these things, the exponents here just add up. But now the good thing is you've made this parameter P, this particle momentum, a parameter of your representation. So you've sort of linked the dynamics of the model with the big symmetry algebra, and this symmetry algebra is now infinite dimensional. So you have, instead of this Lie algebra, which was just n squared dimensional, you now have an infinite dimensional algebra, which certainly gives you a lot of symmetry. So, well, and then maybe I can just mention one curious feature. And then stop. So as I just said, the momentum becomes part of the representation, which is good, and we have an infinite dimensional symmetry, which gives us lots of constraints. So consider, for example, a two-particle state. Let's say PA PAQB, I just separate the two factors for a while. So this is just a standard two-particle state. And now we act with, let's just act in the standard way with this generator, JA M on PA QB. So in a tensor product, you would do the following. JA M on PA times QB plus PA cross J AM QB. Okay, so using this action down there, here we get U of P to the M times JA acting on PA cross QB, and here you get UQ of M J, now P A times QB. And well, the crucial thing is that this factor is in general different from that factor. So whereas before, say this factor wasn't there, then if you symmetrize these indices A and B, then the symmetrization would go through the action of the generator. But now you have different factors in front, so so this will typically be sort of irreducible. If you project if you project to the symmetric combination, say, on either of these two, then after acting with the Lie generator, this is still respected, but here this will be irreducible.
How about one more J?
Oh yes. Thanks. Okay. The only exception in this case would be if the two particle momenta are the same, PA and PB, then you get this as an overall factor, UP to the M, and here you act with JA on the two particle state, PA, PB. And so if you symmetrize here, you would get the same symmetrization afterwards. And so only if the two particle momenta are the same, you get an irreducible. You get this tensor product to reduce to be decomposable, whereas here it in general doesn't decompose. So if you then go back to something I wrote down earlier. Well, we had the R matrix being sort of R symmetric times a symmetric. Well, I didn't quite write it that way, but just because the tensor product of two fundamental representations could be decomposed, I got two different factors. You could write it as this. Some factor for the symmetric part times a projector on the symmetric part times something for the antisymmetric part times a projector. But now, in general, these two particle or multi-particle representations will be irreducible. So here here the analog would be would just be, well, irreducible. I mean, it's just one representation. So you would write, so the R matrix would be just given as some factor times, if you want, some intertwiner which is uniquely defined. So that means if you have this big symmetry algebra, then the tensor products will typically be irreducible, and therefore the R matrix is already uniquely defined, and you don't have to go through all this problem of a nonlinear equation.
Is the Yang-Baxter equation then automatically obeyed because as a
Yes.
consequence of this? How about the opposite implication? Is there any direct relation between integrability and this algebra? In other words, do generic integrable systems have this symmetry, or?
Generic integral particle models should have a symmetry like this, although I can't really explain why.
Are there situations known where it's actually a symmetry of the underlying Hamiltonian? For example, say Heisenberg's spin chain or something like that?
This is actually almost a symmetry of the Hamiltonian because, well, it commutes with the Hamiltonian up to boundary terms, which you don't care for on an infinite chain or infinite system string. And there are some Hamiltonians, like Haldane-Shastri Hamiltonian, with which this symmetry commutes exactly. I don't really have a good reason why, but it's certainly good to have a big symmetry algebra which gives you irreducible tensor products, because that alone by the symmetry gives you a unique answer, and hopefully this answer obeys the Yang-Baxter equation. You can probably derive that in a few lines, I guess, but I don't quite recall how it's done. But I think it's a good time to stop, and perhaps next time I can continue with the Yang.
Are any other questions? Okay.
What happens if you have a central term in this algebra?
I'm sorry, it was...
Similar algebras may have central terms. If you have central terms.
Right, there could be a central term. However, for the evaluation representations, you can't have a central term, I think. The evaluation representations typically have no central charge. But I guess the centrally extended algebra does also play a role in integral models. Maybe not for this particle model at this stage, but maybe for vertex operators, or I don't know what.
Any other questions? Okay, let's thank Niklas again.